All right, let's talk about one of the most fundamental and, let's be honest, most misunderstood laws in all of physics. It's the hidden rule that explains why time only flows in one direction, why your hot coffee inevitably gets cold, and it even predicts the ultimate fate of the entire universe. Today, we're diving deep into entropy.
So think about this for a second. We've all seen an ice cube melt in a glass of water. Happens every single time. But have you ever seen a puddle of lukewarm water just decide to gather all its energy together and freeze itself back into a perfect ice cube? Of course not. It seems totally obvious. But when you really start to ask why, you stumble upon one of the biggest mysteries in science. Why is our world a one-way street?
And here's where it gets really weird. If you could zoom in and watch a single water molecule bouncing off another one, that interaction is completely reversible. You could play the film forwards or backwards, and it would look totally normal either way. The laws of physics down at that tiny level don't care about the past or the future. So if the microscopic world is a two-way street, what gives? Where does this unstoppable arrow of time that we experience actually come from? The answer, as you might have guessed, is entropy.
Okay, so to get to the bottom of this, we need to completely shift our thinking. Forget about forces or mysterious pushes and pulls. The secret isn't in physics as you normally think of it, it's in probability. It all comes down to simply counting all the possible ways things can be arranged.
Now, you probably heard entropy described as disorder or randomness. And look, that's not totally wrong, but it misses the beautiful simplicity of what's really going on. A much better way to think about entropy is this. It's just a count. It's the number of different ways you can arrange the tiny microscopic parts of a system, the atoms, the energy packets, that all end up looking exactly the same from the outside, from our macroscopic view. It's a measure of possibilities.
To really wrap our heads around this, let's use a fantastic analogy. Imagine little packets of energy are like sheep, and the atoms inside an object are like separate plots of land or little farms. How energy spreads out among atoms is a lot like how a bunch of sheep might randomly wander and arrange themselves across these different plots of land.
Okay, so if you have just a few sheep and a few plots, the number of ways they can be arranged is pretty small. You could count them. But watch what happens as you add more. The number of possibilities doesn't just add up, it explodes exponentially. By the time you get to just 30 sheep and 30 plots, you're at 59 million, billion possible arrangements. I mean, it's a number so mind-bogglingly huge, it's hard to even comprehend. Now let's look at what these arrangements mean. If we have, say, two big farms, what are the chances that all the sheep are bunched up in one versus being spread out pretty evenly between the two? Well, it turns out there are just vastly more ways for the sheep to be in a spread-out state. The state where they're all concentrated on one side has very few possible arrangements, while the spread-out state has hundreds more.
And this right here, this is the absolute key. Get this, there is no mysterious force pushing the sheep to spread out. There's no law of nature that says sheep must be evenly distributed. It's just statistics. A system, when left to its own devices, will naturally and randomly wander into the state that has the overwhelmingly largest number of possible arrangements. It finds the state of highest entropy because it's just the most likely outcome, by a long shot.
So if it's all just a game of chance, a roll of the dice, how does this simple tendency become an ironclad, unbreakable law of thermodynamics? Well, it all comes down to scale.
You know, what's really fascinating is that in super tiny systems, this law can actually be broken. If you only have a handful of sheep, it's totally possible that just by random chance, they could all wander back into one farm for a moment. This means that at the microscopic level, entropy can and does decrease sometimes. It's a fluctuation, and scientists have actually seen this happen in experiments.
But look what happens when we just scale it up a little bit. For a tiny system of just 50 atoms, what are the odds that all the energy would spontaneously bunch up in one half? The chances are already about 1 in 133 billion. Incredibly unlikely.
Now imagine something you can actually see and hold, like that ice cube. We're not talking about 50 atoms. We're talking about trillions upon trillions of them. The odds of all those molecules arranging themselves back into a low-entropy, frozen state become so astronomically small, they might as well be zero. It is just not going to happen. An unlikely probability becomes a virtual impossibility. And that is the second law of thermodynamics. It's not a rule for a single atom. It's an emergent law of large numbers.
The great astronomer Arthur Eddington put it perfectly. He said that this relentless statistical march towards the most probable, most random state, that is what gives time its direction. The past is, by definition, the state of lower entropy, and the future is simply the direction things are most likely to go, towards higher entropy. So this arrow of time isn't just some abstract concept, it has very real, very practical consequences for energy itself. It turns out it's not just about the amount of energy you have, it's about the quality of that energy. We all learned the first law of thermodynamics in school, right? Energy can't be created or destroyed. The quantity of energy in the universe is fixed. But the second law, the law of entropy, introduces a crucial twist. It tells us that energy also has a quality, a usefulness, that scientists call exergy. And here's the kicker. Unlike the quantity of energy, this quality, this exergy, is not conserved. In every single real-world process, some of it is always destroyed.
So what exactly is exergy? Well, think of it as the get-stuff-done potential of energy. It's the part of the energy that can do useful work, like power your car or charge your phone. Concentrated, ordered, low-entropy energy, like the chemical energy in gasoline, has really high exergy. But spread out, disordered, high-entropy energy, like the waste heat coming off your laptop, has very low exergy. It's still energy, sure, but its ability to do work has been ruined. So how does this useful energy get degraded? Well, let's zoom all the way back down to the atomic level. One way it happens is through a process called impactrans. Imagine the organized, useful kinetic energy of a hammer hitting a nail. That impact causes electrons in the atoms to get excited and jump to higher energy levels. But they can't stay there. When they fall back down, they release that energy, not as organized motion, but as random vibrations and radiation, which we feel as heat.
And it works the other way around too. When an atom absorbs energy and an electron jumps up, the atom itself actually gets a little bigger, pushing on its neighbors. This turns potential energy into more of that random, jiggling kinetic energy. The point is, these little transformations are happening all the time, everywhere, and the net result is always the same. Useful, ordered energy gets converted into less useful, disordered heat. This constant degradation of energy quality sets some very hard limits on what's possible in our universe. It's why, sorry inventors, perpetual motion machines are absolutely impossible. You always lose some useful energy as heat. It's why your car's engine can never be 100% efficient. A huge chunk of the high-quality energy in gasoline is inevitably wasted as low-quality heat. Useful energy is always being lost.
Okay, so this brings us to our final and maybe grandest perspective. What does this relentless, unstoppable law of increasing entropy mean for the universe and for us?
You can actually think of the entire history of the cosmos as one long journey up a massive mountain. Let's call it Mount Entropy. The universe began at the bottom, in the incredibly ordered, low-entropy state of the Big Bang. And ever since, for 13.8 billion years, it has been relentlessly climbing, spreading out, and moving towards the peak, a state of maximum entropy, maximum disorder, sometimes called the heat death of the universe, a final, perfectly boring equilibrium where nothing interesting can ever happen again.
But we're not at the peak yet, and in the meantime, while the universe is on this climb, something incredible is happening. As the thinker Steven Pinker puts it, life itself almost seems to have a purpose, to fight back against this cosmic tide, to use energy to carve out these little pockets of incredible, beautiful order. That's us. That's every living thing on Earth. We exist here on the slopes of Mount Entropy. And we're able to build our complex bodies, our cities, our civilizations, because we're cheating. We have a massive external source of high-quality, low-entropy energy, the sun. We take in that useful energy, use it to create and maintain our local order, and in the process we pay it back to the universe by spitting out even more entropy in the form of waste heat, actually accelerating the universe's overall climb. Our order is borrowed, and it's temporary. And this leaves us with a final and pretty profound question to think about. If we know the universe's ultimate fate is disorder, and if everything we build, everything we are, is just a fleeting pattern on this grand journey toward equilibrium, what does that mean for us? What should we do with our brief, beautiful moment here on the sunlit slopes of this cosmic mountain? That's something to chew on. Thanks for joining me for this explainer.